Lesson 10.4 Magnetic Fields Produced by Currents. To do this, we use Ampere's law, the guy that the unit of current, the amp, is named after. Oh, that's a calculus definition. It says the sum of the magnetic field vectors dot product with little tiny bits of length equals a constant times the current inside. Now we call this little bit of length a path. And the I's are the currents inside the path. All right, so if we drop the calculus a little bit, we want the magnetic field component that's parallel to our path. And we add those up. Well, it's easier if we use symmetry. So we're going to use symmetry. B is the magnetic field. The B with the two little parallel marks is the B field parallel to our path. And the delta L is a portion of a path that surrounds the current. The constant, mu0, is the permeability of free space, just 4 pi times 10 to the negative 7 Tesla meters per amp. And I is the current enclosed in the path. So in our picture, the current would be both of those. Again, symmetry works well, so we're going to use simple things. So let's look at a single wire. Our path around the wire, if we make it simple, is just a circle with the wire at the center. So its distance would be the circumference, 2 pi r. So to solve for that magnetic field, I'll divide by 2 pi r, and we have the magnetic field due to a straight wire. Now, the direction of that magnetic field is actually circular. If you use your right-hand rule, we had magnetic field, current, and force. But this time we don't have a force, so it's actually another right-hand rule. What you do is you curl your fingers of your right hand and put your thumb in the direction that the current is flowing in the wire, and that shows you either the direction of the current or the direction of the magnetic field. Take your right hand, pretend like you're grabbing the wire, your fingers curled around it, and you'll see your fingers will curl that way. So your magnetic field around a long straight wire is circular. Alright, so let's talk about that again. Oh, this time with better pictures. So your right hand rule. Grab the wire with your right hand. You might want to try using your pencil to see. So grab your pencil with your right hand. Your thumb points in the direction of the current. That's just like in the other right hand rule. And your fingers will curl in the direction of the magnetic field. So just like the other right hand rule, your fingers are going the direction of the magnetic field. So you can see there in that picture, the magnetic field is actually circles around the wire. And the formula again. If we use a loop, we talk about the magnetic field at the center of the loop. That's where it's strongest. So when you grab your loop, you put your fingers in the middle of the loop. So you might want to curl up a charging cord, or you can use a hair tie rubber band. Put your fingers at the center, and your thumb will naturally lie along the direction of the magnetic field. Or sorry, your thumb goes the direction of the current, fingers are the direction of the magnetic field. Fingers at the center of the loop, your thumb will lie on the wire going the direction of the current. And its formula, the magnetic field for a loop, is N mu 0 I over 2 times R. R is the radius of the loop. N is the number of loops. A solenoid is like a really long stretched out loop. It's a bunch of loops right next to each other and makes this long tube. And you get magnetic field is mu 0 Ni. Notice it's a lowercase n. N is the number of loops per meter, so it's your loop density if you'd like. And a solenoid gives you a very strong magnetic field in the center if you run current through it. Let's try an example. A long straight current carrying wire runs from north to south. A compass needle is placed above the wire and it points with its north pole towards the east. What direction is the current flowing? There's my wire. My compass is on top of it with its needle pointing towards the east. So grab the wire with your fingers going in the direction of the magnetic field. So your fingers above the wire, so on your side of the wire, is going towards the right. That'll make your thumb point up. So that means the current is flowing towards the north. If the compass was put underneath the wire, which direction would the needle point? Well, pretend that you're grabbing the wire and your fingers are going to go the direction of the magnetic field. They're going to curl around. So your thumb's going up. Your fingers are curling around that, and you can see on the back, the compass would be pointing towards the left. That would be west. A single straight wire produces a magnetic field. Another wire is parallel and carries an identical current. The two currents are in the same direction. How would the magnetic field be affected? So there's my two wires. There's the magnetic field from the first wire. I have the current going up. So you pretend like you grab the wire and the magnetic field is going to curl around that way. It comes out of the page on the left, goes above the wire, in front of the wire, and then going towards the right, and then into the page on the right side. There's the current and the magnetic field for the other wire. You can see, oh, and there's one, the magnetic field due to the left-hand wire. I just have it extended around the other wire. So you can see in the middle here, we have one magnetic field going in, the other magnetic field going out. So it's like a negative and a positive. Well, if I add those together, it's going to be something less than either one. Over here, both magnetic fields are going into the paper. So that's the one from the right wire. That's the one from the left wire. Both going in, so they would add. So the B fields between the wires would cancel out, and outside the wires they would add. What if the currents were in opposite directions? There's my wires, the current's going opposite directions. The magnetic field from the first wire, your thumb is going up, your fingers curl around it. Think of grabbing a pencil with your thumb going up, your fingers curling around. And that's the magnetic field for the other wire. This time put your thumb down and curl your hand around. It's going the opposite direction. And that is a magnetic field from the left-hand wire going around the right-hand wire. You can see in the middle here, both magnetic fields are going into the paper. So they're going the same direction, they'll add. Over here, the magnetic fields, one's come out, the magnetic field from the right wire is going out. The magnetic field from the left wire is going in. Those will cancel. So the magnetic fields between the wires add, outside the wires they cancel.